Good evening. I'm Yvonne, Staff for Science for the Public, and I welcome you to our Contemporary Science Issues and Innovations program. Tonight, we hear why our planet depends so much on the health of its oceans. Our guest, Amala Mahadevan, is a senior scientist in physical oceanography at Woods Hole Oceanographic Institution. She's an expert on the complex physical, chemical, and biological aspects of the ocean. She also leads research and expeditions in ocean dynamics. As a matter of fact, she's getting ready for an expedition very soon. And she has also developed models that predict and explain these complex ocean processes. Dr. Mahadevan appeared on this program in 2015 to demonstrate mechanics of phytoplankton blooms in the oceans, which are important in the absorption of the atmospheric CO2. And we are so delighted and honored to welcome Dr. Mahadevan back again. Welcome.
Thank you.
And I would like to start, if we could, with just a little background. I think that most of us think the oceans are just out there and that there are not necessarily systems, dynamics that we need to know about, and you're the expert in the dynamics. Could you give us a little background about how oceans work?
Yeah, so the oceans are, hold an enormous amount of water. 97% of the Earth's water is in the oceans.
Yeah.
What we see on land is just a very minuscule amount. And they are constantly in motion. So the ocean is forced by the winds. The winds cause the currents, and the currents are caused by a combination of processes. One is that the winds put mechanical energy into the oceans. And the other factor is that you have the continents and the shape of the basins that constrain the flow and create boundaries. The third thing is that you have differences in density of the water, and those differences in density also play out as differences in pressure. So when you have light water versus more dense water sitting next to each other, that leads to currents or jets in the oceans. And furthermore, importantly, the oceans are on a rotating planet, and the dynamics is very much affected by the fact that the planet is rotating, because we are on the rotating planet viewing everything in that rotating frame.
I see.
And so because we are viewing it in the rotating frame, there is the effect of rotation that we see keeps turning things, to the right in the northern hemisphere, left in the southern hemisphere.
Right.
And that's what shapes the currents, and the oceans are not at rest. I mean, if you look at a forest and you go and look at the trees, you come back and you measure the same place, the same tree will be there. But if you go and look at the oceans, you measure one part of the oceans today, you come back tomorrow, that water is gone, it's moved away, and you have other water. So it's a challenging environment to work in, but also very interesting because everything is in motion
all the time.
That's
all
right.
the time. So, so there's a physics to this process,
absolutely.
right? You mentioned pressure. What about like temperature differences in the different areas of the planet? Does that affect these processes too?
Yeah. So the pressure in the ocean is set by differences in sea level, which might occur, for example, because of the wind blowing, and then you have a continental boundary. So for example, if the wind blows and it moves water away from the continental boundary, it can pile up at the other continental boundary. So that's one way in which you generate pressure differences. And you also can generate pressure differences when you have differences in density of the water, which come from temperature and salinity. So the two factors that control the density of seawater are temperature and salinity. I would say in a large fraction of the ocean, it's temperature that dictates the density. But in places where you have a lot of freshwater runoff, or when the water is very cold, like at the high latitudes, the Arctic and Antarctic Ocean, you get the effects of salinity being more important on the density.
Oh, I see. So it depends on where you are and temperature. So there are multiple facets each time to consider.
Right. Yes.
In terms of these currents, we hear a lot about this. We're hearing a lot about temperature, salinity, and the currents that we kind of depend on for as far as a lot of ecosystems and so on. Could you give us some idea about how these currents work, these major things like the conveyor belt and what happens there?
So the surface ocean, as I said, is driven by the wind, and it has a circulation. And each of the hemispheres has gyres or closed currents. So if you look at the northern hemisphere, we have boundary currents which go up the coast. And they are called western boundary currents because these currents get intensified. For example, the Kuroshio is one of them in the Pacific, and in the Atlantic we have the Gulf Stream. And those boundary currents then go up the coast and they break away from the coast and they go across the Atlantic. For example, the Gulf Stream then goes across the Atlantic to Europe, and then it forms a closed kind of gyre-like circulation. That's called the subtropical gyre. And then you have another gyre, which is called the subpolar gyre, which kind of meets that one and forms a closed circulation in the north of the subtropical gyre. Similarly, in the Southern Ocean, southern hemisphere, you would have similar gyres. And each basin has those gyres, but the gyres form intense currents. Most prominent ones being on the western margins, but in other regions too, you have these currents which form a very complex network of branching out, and they form instabilities. So the current is not a straight flow. It starts to meander, and it breaks off into eddies and swirling motion. So if you look at the flow field from above, which now we can do using satellites and also using models, you'll see that these currents break away and form a lot of swirling motion or eddies. And so one of the things that's very classic about the ocean is the swirling or vorticity, as we call, which is the rotating motion of it. Those currents are less intense as you go deeper. They're strongest at the surface. You do get deep currents, but they are not at the same speeds as the surface currents or the surface flows. So there's a strong vertical gradient in the upper ocean of the flow. And there's also a very strong change with density. So the surface is obviously lighter because the less dense water would be more buoyant and stay at the surface, and the ocean is very layered in density. And once you're away from that surface layer, which actually gets well mixed by the wind, then the interior of the ocean is really fairly quiescent in the terms of it's not mixed three dimensions. It's horizontally moving this way. And the flow follows the layers of constant density. So flow moves on what we call isopycnals, which are layers of constant density, and you don't really mix things across layers of density very easily.
Let me ask you, we hear a great deal about like the conveyor belt, for instance, up the American coast and so on, but these things are apparently really significant for maintaining the health of the oceans generally, certainly the ecosystems. What does that mean? How does that work? How does that kind of are there many conveyor belts, and is that the same principle?
So the conveyor belt, people frame this, I think this word was framed by an oceanographer called Wally Broker and some time ago. But some people have kind of pushed back a little bit on the term because it's not like one conveyor belt. It's made up of lots of currents. And it's associated with a very slow overturning circulation. So if you look at the North Atlantic, there are specific regions in the world's ocean where the water becomes dense and starts to sink. So the North Atlantic, the high latitudes in the North Atlantic are one such region. They're a region of deep water formation. And the water there in the winter, it's very salty, that water. And when it starts to cool, it's also salty, it becomes denser. And that water being denser starts to sink and come down as a deeper layer in the Atlantic Ocean. That flow, which is deep, is very, very slow. It takes a long time for that circulation, and then that water is thought to rise in the oceans, and it's not known exactly where because it's not. That's why we afraid to call it a conveyor belt because it's not
Newer
one branch
knowledge
of rising.
is just right.
It has
much more
to,
diffuse.
Yes. In fact, it's raised some interesting questions as to how does that water come back up?
I see.
Or what are the mixing processes, or where does it come up?
All right.
There's a gradual upwelling at the equator, and then that water spreads polewards.
Yeah.
Again, in these currents, one of them being the Gulf Stream,
Right.
but there are other motions by which eddies, and it's very complex flow.
Right.
So in the northern hemisphere, it goes northward, that flow in the southern hemisphere southward, on the whole, transporting heat from the tropics towards the poles. And that's very important because the Earth receives more incoming solar radiation at the tropics
Right.
on average.
Right.
That heat has to be distributed to the poles.
I see.
And so that distribution of heat occurs both in the atmosphere and the ocean. The atmospheric eddies transport heat,
interesting.
and the ocean currents and eddies transport heat.
Right, so
polewards.
that is really important for stability for the planet, I take it, right?
Yes, so we think that during glacial times, the last glacial about 20,000 years ago, we think that this poleward transport of heat was less or cut off, and that the conveyor belt or the overturning, it's called now the meridional overturning circulation, was weaker, and so that transport of heat was weaker, and that allowed the ice caps to form on the poles. Yeah.
And now, with the pole melting, especially the Arctic region.
Yes, so right now, we really don't know how the meridional overturning circulation is changing.
I see.
And there are a number of conjectures with the ice melting in the Arctic. The surface ocean is becoming fresher. If it becomes fresher, the thinking is that maybe we don't see the same rate of deep water formation, and we may slow that. But if we were to slow it, would we change the transport of heat to the poles? At the same time, the oceans are warming, and the region that's warming the most is in fact the Arctic Ocean, the northern hemisphere, and the northern latitudes.
Right.
It's warming the most because of the ice feedback. So without any ice, the ice is retreating every year. We have less and less ice and less multi-layer ice in the Arctic. And ice is white, it reflects heat. The oceans are dark, they absorb heat. So there are these effects of competing
at one time.
Yeah, and so the oceans might warm, and if they are warming rather fastest at the high latitudes.
Yes.
And so we don't quite know how that would change the meridional overturning circulation. And there are some measurements that are ongoing where people are trying to estimate that, but the record is not long enough for us to make conclusions.
I understand you don't have a historical thing to measure that against. And is there a concern that it slows down this process where the warmer comes up and then goes under and creates this sort of conveyor, even if it is diffuse? Is this a potential destabilizing mechanism in the world's oceans? I think a number of certain fish migrations depend on this, but I'm not sure that it slows these things down considerably.
Yeah, it's really hard because it's not one current.
Yes, I understand.
It's hard to say what's,
Right.
So you have to integrate over many motions to try and say what is the meridional overturning circulation.
That's really interesting because what we see in the general media with this, it's one sort of line and it goes under and stuff. And what you're saying is we know better now that this is sort of dated. A dated model of that.
It's a simplified model.
Exactly. And that it is, in fact, more complex, but also that it takes some time to study these things and we don't have a full reckoning of this.
That's
what's going to happen about this.
Because the feedbacks are so many in the ocean, in sort of the oceans and Earth system, ice feedbacks, albedo feedbacks. Salt plays a role as to whether you might form deep water or not.
Yes,
dense water.
Say yes.
The dense overturning circulation depends on what the salinity is, what the heat loss is. The winds matter because the winds come into play.
Right.
And so I think it's quite complex to say.
It is. It's a complex system, period.
Yes,
I just have to ask it because we deal with people who are highly specialized all the time, and everybody in, say, oceans or whatever, everybody is studying a slice of
Yes.
something. And in so many fields, you need a lot of minds together
That's right,
anymore,
yeah.
combined to get to something. But in your opinion, is there like a reorientation to deal with complex phenomena like this? Because this is extremely complex, the way you're outlining it.
Yeah.
Like in terms of training young people to go into these fields, are they looking at things? Your perspective is complex. You know, your background is. So
Yeah,
we'll just,
I think students are now much more multifaceted than
Yeah.
what we were,
Right.
trained to
Right.
be before. And models have improved a lot. You can do a lot with computational models. The observations have improved a lot because we have a lot of autonomous instruments in the
Yes.
ocean which are sending data back to us. And our ability to get data from satellites has improved.
Yes.
The thing that we don't see a very much of a upward curve on is the funding, because and
I
the
know,
budgets kind
small
of stay
things,
stay
and
flat.
just at this time when you really need it.
That's
And does it take like long-range studies? This is a problem
Yes.
in many fields. You
Yes,
get
that's right.
grants for 3 or 4 years, but you need 20.
That's right.
So they-
Especially
yeah.
Long-term time series really
Yeah.
help to try
Yes.
to document what kind of changes are there.
Right.
But also you need good baseline measurements. So trying
Yes.
to get measurements everywhere in the oceans is also important.
Right.
So it's very, very undersampled, the oceans, as you can imagine.
Because it was so vast.
It's vast.
And stuff.
It's really
Right.
vast, right? It's 72% of the Earth's surface is covered by the
Exactly.
oceans.
And with
but
all
how
these
often,
changes,
yes, yeah.
with all
and
these-
going at one time and making one measurement doesn't tell you how it
No,
is there tomorrow, because
right.
it's a different.
Exactly.
You cannot go back to
exactly.
the same water mass or the same place and expect the same water to be sitting there. So
Right. I want to come back to this business of the equipment that you have now at hand, but before that, what does it mean to destabilize? What will happen if the oceans are destabilized? And I imagine there are a number of ways that can happen, the salinity, the temperature, all of that, but what will happen to the planet if, what can we take?
yeah, so certain things would always be stable, in the sense that
Yeah.
there's always going to be lighter water at the surface
Yes.
and denser water at depth.
Right.
So now when you warm the surface oceans, then you have more light water at the surface
Yes.
and dense water at the depth. So the density difference between the surface ocean and the deeper ocean increases. That is in fact adding stability to the oceans.
Oh, it is?
Yeah.
Okay.
In the vertical. So there's different kinds of stability.
right, I
There's so many
understand, I
kinds of
understand.
stability. But if you increase the density gradient in the vertical, then one of the concerns is that you won't be able to upwell nutrients as easily, because now there's
because the nutrients are,
are down below.
Right.
So that's one kind of possible effect, that as you warm the surface
Right.
oceans, will our phytoplankton production or
exactly, which
productivity
every
keep
the
up
basis
with us?
there,
Yeah.
right?
Another kind of thing which you might depend on is this, as you mentioned, you have to form deep water somewhere, or dense water somewhere,
Yeah,
for it to sink
right,
and
right,
overturn.
right.
And so we don't know whether we will maintain the same rates of dense water formation for this, keep up this meridional overturning circulation at the same rate, or we would change that rate by actually warming the Arctic Ocean or the northern, the high latitude
Yeah,
ocean,
right,
essentially.
right.
So that's one concern. And another would be that as you change the gradient from the equator to the pole, the temperature gradient, because the poles are warming
Right,
faster than the
right,
equator,
right.
then the horizontal density gradient also differs,
Okay.
changes. And we don't know what the effect of that is. Typically, the larger the horizontal density gradient, the more scope for instabilities or eddies.
Okay.
So the higher the density gradient in the horizontal, from between pole and equator, we think we'll have more eddies and more heat will be transported to the pole. So this is a sort of a a negative
Yes.
feedback. So
Yes.
there's some things which have a positive feedback,
I
like sea
understand.
ice,
Right.
and some things which have a negative feedback
Right.
on trying to correct the system.
Okay, so this general heating of the ocean and the general buildup of CO2 are those mechanisms that they watch very carefully, that because are those like major destabilizers or
Yes,
Or does it depend on
stabilizers
where?
or destabilizers, depending on how you look at it.
Yeah.
So the oceans are warming.
Yes.
Almost by a degree they've warmed on
Right.
average, the surface ocean. And when people talk about global warming, I think people don't understand that where, people look around and say, but it's all right, it's still cold today, when we walk out.
Weather,
Yes,
confusing the
which
weather.
is very
and that.
different.
Right.
Because most of that heat of global warming, 97% of that heat is in the oceans. And so people are trying to estimate how much heat has gone into the oceans in the last, few decades.
Right.
And there's a number of new estimates that have come out, and they all agree to some, fairly well, in the sense that there is a lot of heat that the oceans have acquired. So the atmosphere, on the other hand, doesn't have the heat capacity of water, it's air.
Yes.
And so the ocean has 1,000 times more heat than the atmosphere. And it's the oceans that are warming, and that's what's changing our climate, right?
Yes.
Or that's what will
okay.
change.
And it doesn't dissipate that easily. Is that the idea, that it doesn't reverse so easily?
The reason the whole planet is warming is that we have more CO2,
Yeah,
which is acting
right.
like as a greenhouse gas.
Exactly.
So you have to raise the Earth's temperature to come into equilibrium, would have to be higher to radiate out to space
Yes.
the same amount of heat that it's receiving.
Okay.
And that's why the entire planet, that's the greenhouse effect, is going to raise its temperature. But where's that heat? That heat
Right.
is all in the oceans.
Right. As somebody dealing with this on multiple levels and stuff, are you concerned about this, or are we being too overly concerned about the direction of the climate change with this?
Oh, no, I mean, there's climate change is seen everywhere, and everywhere, especially in the oceans,
Yes.
The region, one of the regions that's warming the fastest is this region off our coast here
Yes.
in Boston,
Yes.
northeast. It's the
Right.
fastest warming region if you look at it spatially. I mean, there's certainly no over-concern. The concern is that we're not concerned. This is the big concern for me.
Oh, you mean like the general, the governments and things
yes,
are not
yeah.
acting
Yeah.
like that?
I mean, it's the biggest problem or the biggest issue that we're going to be faced with, that humanity is going to be faced
and
with.
that is that the oceanographers, people in your line of work, do take this very seriously.
Oh,
are
of course,
definitely
yes,
concerned
yes.
about it. But the question is how to get it studied more, and
Yes,
how to get
yeah.
how to get the governments really to pay
Yeah.
attention to these problems.
That's right, yeah.
Technically, is it reversible still?
So when you say climate change,
No, I meant specifically the oceans, the warming of the oceans, for instance. Are we in a position, if we put our minds to it, if there were a policy, could they slow this down or whatever?
yeah, so if we stop producing more CO2, I mean, the rate at which we're putting it out is increasing,
Right,
and if we
okay.
stop producing it, then we would, try to arrest that.
Right,
But
so
we are, so we would try to, makes a huge difference what trajectory we take from now into the next
Okay,
25,
that's
30
what I
years.
was kind of after,
A small
that you-
change in our behavior could cause a huge change up ahead, because it's a question of whether this trajectory goes up like this or
Yes,
like this. And
yes.
so they all diverge, and so whether you see a 2-degree change or a 3-degree
Right,
change or a 4-degree
right,
change
right.
is all based on our behaviors
Right, but
in the
it
next few
depends
years.
on
Yeah.
people making a policy
That's
and then
right.
following through on it. I'd like to go ask about this wonderful, the way you study these things now, the way we see these things bobbing up and down in the oceans and
yeah.
stuff, and people can go and check them periodically and so on. But you mentioned satellites, equipment in the oceans, and apparently this is very sophisticated. Can you give us some examples?
Yeah, so with satellites, you can measure the sea surface height or the topography of the sea surface. And those satellites, by measuring the height of the sea surface, so of course there's all kinds of effects in there, and if you remove the effects of waves and things, then you get the pressure. For the height of the sea surface is telling you where you have high pressure and where you have low pressure. And so based on that, you can get a picture of what the surface currents are, not at very high resolution, but at
it's still a lot better than
over degrees,
Yes,
latitude and
right,
longitude.
right.
You can get a picture of the currents
Right.
and the circulation
Right.
at the surface of the ocean.
Yes.
You can also look at sea surface temperature from space. So we have different kinds of instruments to look at sea surface temperature, and so we can monitor that and look at changes from one season to another, from one place to another, and that data is available at fairly high resolution, as much as a kilometer resolution. And you can also look at the color of the ocean surface. So we have something called ocean color satellites, which are looking at essentially can give you ideas of what the chlorophyll is, for example.
Yes,
or
right.
what's being scattered
Yes,
back from the
yes,
ocean.
right,
So you can
right.
estimate, again, looking at the surface, so you can't look at the layers which are very deep,
Yeah.
but you can try to estimate what the
Right.
productivity, the primary productivity of the ocean is
Right.
based on some of these satellite products. They all have caveats, but
Yes.
we also have one that tells us the salinity now. So
This is just
yeah.
satellites that
That's
doing
right.
that.
Yeah. People are working on other satellites to tell us the velocity of the water, better.
Right,
And so
right,
there's a number
right.
of things which are sort of in the works. That satellite, and then people have to go and make measurements in situ
right.
in the water.
Yeah.
In fact, those are used also to calibrate the satellites. Satellite
Right.
measurements are always
of
an
course,
estimate.
Yes, yeah.
And so we send ships out to sea, but ships can only make a few measurements. So we have a lot of autonomous instruments. One of the most successful programs is one called the Argo program, which floats. So floats are things which are can be subsurface in the
Yes.
ocean. There's floats are about like big long cylinders,
Yes,
this height,
right.
and they are programmed, these instruments, to go up and down in the ocean. So they park themselves typically at 1,000 meters depth,
Yeah.
and they're freely drifting. They come up to the surface and they measure in the vertical a profile of temperature and
yes.
salinity, and they come to the surface and beam that data back to satellite, which we pick up.
That's
in our
really
lab.
incredible.
So now there are thousands of these floats which are seeded the ocean, and we're getting this data back in real time. And different countries have cooperated in putting these out.
Right. Two things about you. You're about to go on an expedition.
That's right.
Is that to check these kinds of things or to do some measurements like what?
Yeah, so the expedition we're going on is to look at specifically the processes that occur at a front in the ocean. A front is where you have waters of two different densities meeting. And so we're going to the Mediterranean, where we have Atlantic water coming in, and the salty Mediterranean water, which has a much higher density.
Yeah.
And that boundary between different density waters is very dynamic. So we have a very strong flow or a jet or a current
Yes,
there.
I see.
That very strong current has instabilities on it, and we are looking to see how things might move up or down
Yeah.
along those density surfaces of that current. So we will be going and trying to make measurements of these at much finer scales,
Yeah.
and then we can see from satellite by actually being there and making the measurements and following drifting things in the water and measuring behind the ship as we're going along. And then coming back and putting these observations into models, we try to understand the processes.
Right.
that lead to
And that's the other thing, is that you developed quite a model. Would you tell us a little bit and how models work? Why? Because I take it that they are able to accommodate these complexities that you have to deal with.
That's right, yeah. So what models are doing is essentially they're solving the partial differential equations that describe fluid flow.
Okay.
They're called the Navier-Stokes equations, and we solve those for the motion of the fluid. They describe, those equations describe, they're essentially Newton's laws, which tell us how something will move and if a force is applied or to it. So when there is differences in pressure, that's one kind of force that you might have. You might have wind driving the surface ocean, you might have it warmer, colder. And so you prescribe these inputs to the model, which is the forcing, and the model is solving those equations. The way we do it is we take the equations and we say at every place in the ocean this equation should be satisfied, and it tells us how that the momentum will change, essentially. The velocity of the water will change with time.
Okay, so it predicts that. That's an important
right.
thing.
Yes, so
okay.
it predicts. We do that by taking our fluid, in this case the ocean. We do the same for the atmosphere. They're very similar, both these kinds of models. And you break it into chunks. So you break it by essentially putting a grid over it. That's one way to do it. So essentially you're solving at every place or location, and every location is connected to the adjoining location, and you're updating the solution in time. So these models require a lot of computational power. With more and more better computers, we're getting better and better models for the atmosphere and the ocean, and better
Which you
models
have to
for
sort
the
of put together, don't you? I
That's
guess
right,
down the
yeah.
down
Yeah.
the line.
And so
right.
there are many flavors of these models. There are a number
Right.
of models that exist, and students nowadays can download these and use them.
Oh, that's fabulous,
right.
isn't it?
Yes, that's
That
right.
is fabulous.
And you can have models that couple the atmosphere and the ocean together, so that you don't have to prescribe the atmosphere to the ocean and ocean to the atmosphere. So that's
Okay.
kind of the state of the art in modeling.
Right. These you're able to accommodate in these models these changes that in flow, but also maybe these other conditions like the salinity, all the heat, all of that sort of thing, and take a look.
Yes, the models need boundary conditions. So the
Yes.
surface is one
Yes.
boundary.
Yes, I understand.
And they
Yeah.
need initial conditions. You start
Yeah.
with something and
Yeah.
you keep integrating in time.
Yeah.
And so, either people do the entire globe. What I do is I try to concentrate on some specific region
Yeah,
or some
right,
process.
right.
And study a particular process which is motivated by what we saw in the ocean.
Yeah. Right. And take it from there. You mentioned that you needed longer range studies and so on. What would be a good length for things that would really study the very changing dynamics of the ocean, the risk kinds of factors now? What would be like a good timeline? Like 20 years or 10 years, we may not have that much time. But
That's right, yeah. I mean, I would say a few decades, when you have a long time series of 20 or 30 years,
right.
then you're
and
able
we
to
haven't
say
had
something.
in the past,
Well, for some,
not for this equipment and so on.
That's right. I mean, there's more and better measurements.
Yes.
And people have reconstructed time series with, for example, sea level. We
Yeah,
have tide
right.
gauge data that
Right.
goes back a few hundred years.
Yeah,
But
right.
then we have better data and better data.
Right,
and so
right,
people
right,
have
right.
tried to combine those records to come up with records of sea level rise
Right.
at certain locations where we have long time series.
Right, right. One of the things I was trying to get at was that this stuff is really complex, that when scientists talk about things like climate change and stuff, we need a picture in our heads of something very dynamic, very complicated, and that you build these models to try to address that
That's right.
complexity as best as possible. But
That's right.
these may be subject to correction or adjustment over time as you get new data.
That's
and
correct,
so
yeah.
on.
So the data that we get feeds into the model.
Right.
And so observations are very crucial in making the models better, or the
Yes.
predictions better,
Yeah.
and telling us whether our models are correct, but also providing the right data
Right.
for the models.
Right.
Yeah.
And what an exciting field.
It is,
and
yeah.
today, just one more thing here. The students are training. You have an ability to look at the physics, the chemistry, the everything there, and it seems reasonable that one has to have that capacity. And you do see this in terms of students coming up today, and also the ability to make models, presumably.
Yes, I mean, a lot depends on the person.
You're right.
One might have a student who has an interest in
Right.
both physics and biology.
Right,
so
but not everybody
not
does. Right,
everybody does. And
right.
for example, the expedition we're just going on
Yes.
next week, we are studying the physics of that current
Yes.
in the Mediterranean. But one of my students is very interested in understanding the phytoplankton community
That's a big thing.
structure.
Right.
And how is that shaped by this very strong front which separates the Mediterranean water and Atlantic water.
Yeah.
And what we're seeing is that these are different phytoplankton communities. There are so many species, just
I didn't realize that.
of phytoplankton out
Right.
there.
Yeah.
And each one has a different effect on how they take up carbon
Right.
and where it goes and what they do in the whole food web.
Right.
So trying to understand the biology and how it's related to the physics is really important, I think.
That's very interesting because that's a absolute basis of life, I guess.
That's right. And
in the
also, if we
oceans.
want to make a longer term prediction of what happens to the carbon in the oceans, the
Yes.
atmosphere, it's very difficult to do that without making a prediction of what will happen to the phytoplankton and the whole
Right.
ecosystem.
Right.
And we don't really know that. For example, will the community change when the ocean is warmer? Will you evolve new species?
Yeah, I was going to say, can it adapt fast
will
enough?
Will it adapt? Will you have new species? Will the
Right.
size structure of the
Right.
phytoplankton change? That will affect how much carbon sinks
Right.
through that biomass into the deep oceans. So the uptake of carbon by the oceans, so the oceans are taking up about a third of the CO2 that we put out now.
Yeah.
And that depends very much on what those phytoplankton communities are doing, as well as the whole ecosystem that's feeding on the phytoplankton.
Right.
So, we'd really difficult for us to tell. We don't understand the biology as well and how it's going to relate to the physics.
Right. And
But,
certainly
yeah.
the adaptability of these very basic species
That's
and
right,
stuff,
yeah.
how fast they can adapt, if they can
There
adapt,
are
where they can
so
adapt.
much diversity in the
Right.
ocean in terms of life. The
Right.
biodiversity in the ocean is immense,
Yeah.
and we just,
We're at the
basically
surface
just at
of
the
it.
surface
Right.
of trying to understand
Right.
something.
What an exciting time to be studying this. A little depressing sometimes, perhaps, but at least it's very helpful for the public, though, for us to know that it is very complex and that you don't have all the answers yet. And so I do hope you get funding and long-term studies out there, that is absolutely
very important,
essential.
yes, yeah.
Right.
Yeah.
Thank you so much for this
Thank you.
wonderful information. It was very interesting, and I wish you the best with your expedition. It's going to be great fun because you said you're going to the Mediterranean. That just sounds
That's
fine.
right. Yeah. So I really appreciate you're doing this, because I think something that people don't realize is how connected the oceans are with our life.
Yes.
Half the oxygen we breathe
Right.
comes from the ocean,
Yeah.
and people don't understand. Most people don't think
Right.
about how dynamic the ocean is and how the physics, the biology, the chemistry is
Right,
coupled,
yeah, right.
and then how it impacts us and our climate
Right.
and the world we live in.
The
Yes.
other thing is that the media could do a better job, maybe, of presenting this if people will listen.
yeah.
That's
Yes,
been a bit of a problem.
but I think-
I was cheered with this reaction of young people, this huge worldwide demonstration of climate
Yes.
urgency coming from the kids, for pity's sake, that maybe this will also increase I wouldn't want to say curiosity, but the demand for good information, that people can understand how this is put together and why we have to pay attention today
Yes.
to this.
Yeah. So you do some very important work.
Thank you. You do too. We really appreciate your efforts. Thank
you.
you so much for joining us. Good
Thank you.
luck on your expedition.
Thank you. Thank you very much.